algorithms library. All right. Today, I'd say is like one of the more like high-level kind of classes where we'll be discussing different algorithms, how to use these different algorithms, and how to combine everything we've known from templates, from Lambda functions, into so that you can use these functions. These functions were written to be as generic as possible, and also to be as flexible as possible, so that they can be used in basically a lot of scenarios. All right. So let's get right to it. So as today's lecture, we'll talk about the algorithms library, which will take us a solid like 20, 30 minutes. And then we'll spend the rest of the time talking about adapters. And then after we do adapters, I have one pretty interesting example about Hamilton, and we'll do that lecture. We'll do that example at the end. Ranges we probably won't get to, so I won't talk about it. All right, who did the homework? No, sorry. Who did the challenge problem I posted on Piazza? Okay, that's fine. That's fine. Like I actually spent some time and came up with a good question. That's fine. So, all right, conceptual review questions. Turn to your partner. Explain what is an implicit interface and how do you figure out the implicit interface. Go. 30 seconds. All right, so just an FYI, instead of candy, I brought these.
Jello shots.
So some people call these Jello shots. Just they don't have alcohol in them. Okay, I don't want to be fired. So yeah, they don't have alcohol in them. Don't worry. Okay, they're really good. That's all I have to say. So and then if you want one, just let me know what color. All right, I'm not gonna bother with the flavors or anything. Just let me know what color.
There are also donuts at the front, which you can pick up on your way out. We won't throw those at you.
Wait, can we pick up yellow shots?
If you answer a question. So, what's an implicit interface? Yes.
It's like the assumptions a program makes when you're like about the inputs, about like the restrictions on them.
Great. So the implicit interface is the assumptions you make about the template parameters. All right. Awesome. What color? Pink. Strawberry. All right. And then how do you figure out the implicit interface? Go ahead. Yeah.
You see what you did with the interface, and then you make assumptions from there.
Yeah. So what you said was you essentially go through the function, look at when that parameter is used, and then try to figure out because we have to do that in this function, that makes assumptions about the parameter. Great. Color? Any? Green. Let's try green. Okay, this is. Oh wow! Let's give me a round of applause. All right. So great. Now turn to your partner. Explain what are predicate functions and why are they important. Go.
So they basically think the shit out of Google, and they're important because I think.
All right. People have stopped talking. So okay. What is a predicate function? Go ahead. Yeah.
It's logic that returns either true or false that you can pass into another function, and that way you can make that other function more general.
Yeah, exactly. So predicate functions are functions which take in some number of parameters and they return either true or false. And they're important because they can essentially make a function more general. Okay. So the reason we did last time, instead of count occurrences of how many elements are equal to some value, you can instead pass in a predicate function, right? And you're returning how many times does the predicate function return true as you're going through the entire collection. Right? Color?
Purple.
Purple. All right, and then lastly, turn to your partner. Why do we use lambdas to create predicate functions? Why can't we just use normal functions? Go.
If you want like store the value like greater than 5 or equal to 5, like make the vocabulary more general, you need the argument to store the value of lambdas just I think.
All right, and who wants to give it a shot? Go ahead. Yeah.
Because it's shorter and concise and limits the scope.
Okay, so let's see. Lambdas are very concise. You don't really want to be building up a separate function, and then they also limit the scope. Limiting scope is an issue, though, right? It is a problem because sometimes you do want the variables in scope. Okay, but that's a good answer. What color? What? Which color? Clear color. Okay, I thought you said beer color, and I'm like, no, these are not shots.
What?
Is this fine?
Sure.
I don't see a clear one, but this is as good as it gets. Good enough. Good enough on my part. All right. I'm also looking for like 2 keywords in the answer. Anyone know what the 2 keywords are? Yes.
It allows you to customize the function without passing a parameter.
Yeah, but without passing a parameter. Exactly. So sometimes you need access to a variable, but you can't pass it as a parameter. Sometimes you are told that this predicate function can only accept 1 or 2 parameters. So you can't just arbitrarily add extra parameters. All right. So great. What color? Okay. Here we go. Oh, that was good. All right. And then the 2 keywords I'm looking for is capture clause. All right. This capture clause allows you to capture variables that you cannot pass as parameters. Okay. And then, so for example, the example that we did over here was we wanted to say, okay, check how many elements are greater than some value. Here we wanted to use the number limit, but we don't actually have limit in scope inside this function. So instead, what's better is to pass in a predicate function which captures that variable limit. Sounds good? Okay. Any questions so far? Yes.
When you say captures, like, can you explain what you mean?
Yeah. So the question is, what do you mean by capture?
Yeah.
Capture just means the variable is currently like in the outside scope. When you create a lambda function, that creates its own inner scope that does not interact with the outside scope. If you want to be able to access the variables on the outside scope, you'd have to essentially put it into the capture clause so that you can access the variables inside the inner scope.
So capture means just put it in the inner scope?
Yeah. Mm-hmm.
Okay.
Yeah. And remember, you can capture it by either value or by reference. Right. Good question. Color?
Sure, yellow.
Yellow. Okay. How many of you did the second part of the homework? I'm guessing none. All right. Yeah. Okay. So be sure to read this. Okay. How many of you looked at this and then decided to not do it? Okay, that's sad. All right. Cool. I will send out more emails just to make sure you all get it. But yeah, we will be using this function today. This is an STL library function. Cool. All right, let's talk about the algorithms library. So last week we wrote a function called count occurrences, and that function that we wrote, that function we don't have to write ourselves because in the STL library there is already a very highly optimized version of what we just wrote. Okay. So if you just ignore the gray ones because those are not super important, you'll see that over here you have a function called count and a function called countif. Everyone see both of these? Count and countif? Yeah. So count essentially is doing what we wrote 2 lectures ago when you just passed in a begin iterator and an end iterator, a begin iterator, an end iterator, and a some element to compare to, right? That's what we have here. Input iterator, and then some const value t. The second version that we wrote, which we did last lecture, is called countif, where we, instead of passing a value, we pass in a predicate function. Okay? And yeah, so this is in the STL library, so what we wrote is essentially up here. Except this is heavily tested and is heavily correct. All right? Yeah, this whatever is in the STL library, you can be assured is as fast as possible and as correct as possible. All right. So whenever you need to do some tasks that are really standardized, like counting how many elements satisfy something, use one of these functions. Don't write your own. Think of these as Stanford library functions, but like everyone uses them, not just Stanford. All right? All right, question, yes?
Just quickly, what do you mean by this one runs in parallel?
Yeah, so if you look at the count or in count if page, you'll see a couple different count if functions. There's another overload of count and count if, which you can actually tell it, okay, instead of running it normally, run it in parallel. I don't want to explain what running it in parallel means. We'll have one lecture at the very end about it. Anna will talk about it. Yeah? All right, here's a map. So there's this guy online who has a blog, and he essentially compiled all the STL algorithms into one gigantic map. Okay, and they're categorized, like over here you can see, let's see, I think this says lands of permutations, land of value modifiers, something about movers, anything else? Algorithms on sets, queries. All right, so these are essentially a bunch of there's just so many algorithms, and they're all listed up here. Each of these little dots is an algorithm. Okay? So, before I get to that, just want to briefly mention some of the algorithms. Some of these algorithms are so useful that there is this corner down here which does algorithms on heaps. And I just want to warn you, just so I don't get in trouble, on assignment 5 PQ, you should not be using these. Okay? Because on assignment 5, if you use these, you can finish the assignment in like 5 lines. Okay? Yeah. Like, your assignment is basically implement this. So do not use this. Okay? If Cynthia tells us why are they using these, don't blame it on me. All right. Let's go do some tasks on a list of students. So what I've done, if you look at the code, is if you look at the code here, what I've done is I have created this struct called student. Each student has a name, has a year, and has a double. We didn't talk too much about, these are called enumeration classes. Essentially, it's just named constants. Okay, so year could be one of 5 different constants: freshman, sophomore, junior, senior, grad. All right? Question, yes? Yeah, kind of like in Java. And we also have a double for each average. Don't worry about this. We'll talk about this next week. All right, and then the other not important parts, I overloaded this operator for you just to make it easier to print. Don't worry about that. This function, read numbers, just returns a list of numbers. Don't worry about that. So read students. You should all know how to implement this by now. So we won't go over it, but essentially takes in a file of all the students. Let's look at the file of all the students. And this is all of you. All right? So this is all of your first names, what year you are, and your grade in 106B. Okay? Cool. Any questions? Okay, oh, they're not like current grades, they're predicted grades. Okay? All right, so let's start writing some algorithms. Okay, so we have 2 parameters. We want to find the min and the max of this list of numbers, and we also want to find the min and the max of this vector of students. Okay, for whatever min and max of a student means. All right, so let's just start simple. How do you find the min and the max of a list of numbers? So if you had to write this normally, how would you write that? Yeah. Mm-hmm.
You would have a variable min max, iterate through the whole list, and then you check whether you found a new minimum or a new maximum.
Mm-hmm. Yeah, great. So essentially do a for loop over everything, check which one's the best. All right. But the STL algorithms already did that for you. You can just write min max of, and then if we go check out the min max the STL library, STL min max, you can see that. What does min max take in? Min max takes in, let's worry about the iterator ones. Where are the iterator ones? Oh, maybe it's a min max element. Whoops. Min max element. There we go. Min max element. And then here you can see that it can take in, let's look at this one down here. It can take in, it takes in 2 forward iterators, first and last, which is basically the bounds of your collection. And it also takes in some comparison function. If you don't pass in a comparison function, it calls this one, where it just compares it normally. All right, so how would you find the min and the max of this list of numbers? If you have your laptop open, try typing in the answer right now. If you don't, think about it. Yeah.
Should we like erase the code that's in min-max test and replace it with what you're writing?
Did I provide the answer to that one? All right. Well, then you all know the answer. All right. Who wants to read the answer off? Go ahead. Yeah.
I mean, you provide the iterator for numbers,
Okay.
the end iterator for numbers,
Okay. So
and then the comparison is normal, so you provide.
sure. So we pass in the iterator for the iterator of begin and the iterator of end, and then we know exactly what the min-max is. What does min-max return? A pair of ints. Let's take a look. What does it return? It returns a pair of forward iterators. Yeah. So remember when we did count occurrences? At the end, we return pairs of iterators. So here, we want to return a pair of iterators, and then we can immediately unpack that by doing this. So we unpack it into min and max. How do I print the min and the max? Yeah, so we have to say the min number is. Yeah, so we can't just write min because min itself is a forward iterator. So you can't just pass that in. You have to dereference it, which actually gets you the number itself. All right? Question, yeah?
For iterators for maxims, you can do min, like first and second.
Mhm.
Does that also apply to this simple iterator, or is first and second only for iterators for max?
First and second are for pairs. So, for example, when you're iterating over a map, when you the elements that you get are iterators to pairs, right? To a pair of key and value pairs. So you would have to first dereference it to get the pair itself, and then using the pair, you can say pair dot first, pair dot second, to get the key and the value.
Okay, so
Yeah.
this is just when the same element is not a pair, so.
Yeah, exactly. Color?
Green.
Green. All right. Okay. We'll see if Anna is better at throwing next week. Okay, and then for max, we did the same thing. The max number is max. Okay? Now, let's say, I'll answer the question just in a bit. Let's say we want to do something for students. Okay, so let's just post it here. Min student, max student. We change these to students. Does this work?
No.
It's not supposed to work. Does it work? Why does it work? Wait. It's not supposed to work. Error message. Yes. Okay. Error message. Okay. So we get this horrible error message. When you get one of these error messages, what do you look at next? We look at compile output, because if we look here, then you can see what the error messages are, okay? So, and then you try to find the line that you wrote. What did we write? Yikes. It's at the bottom? Oh, here, okay. No, these are warnings. Template parameter ignored. It's one of these, basically. Which one? Oh, here. Okay, so it says here that a min-max template is requested. Okay, essentially the key idea here is the error is occurring at this comparison function. Okay, the issue is C++ doesn't know what it means for one student to be less than another student. Does that make sense? When you write your own custom struct, if you don't specify how two students are compared, then it doesn't know what you mean when you say one student is less than another student, right? And there are a couple ways to compare students, right? What is one way to compare students? Yeah.
Their average grade.
Okay, yes, that's like the natural way to do it, right? Because we don't care about anything else. Any other ways?
Names alphabetically.
Okay, names alphabetically. Any other ways? Okay, what year? Yeah, you can also compare them based on year. Okay. What?
The length of their name.
Okay, yeah, you can do that too. Just lots of different ways to compare. So we have to specify how we want to compare. And how do we do that? How do you write a function which determines which one is larger? We want to write we want to write a lambda function. Okay? What should the parameters of this lambda function be?
2 students.
2 students. Okay, and then what should it return?
The greater one.
Yeah, and then you have to specify what does it mean to be the greater one. All right, so here, auto compare student. That's equal to, just remember what the syntax is. The first thing is the capture clause. We don't have to capture anything. As the parameter, we pass in 2 students, s1 and const student s2. And then what should we return? Think to yourself, 15 seconds. All right, anyone? Yes.
What did you say you were comparing using their names
Oh,
or?
sure. Do you want to compare by the averages? Okay, then how would you compare by their averages? Mm-hmm. Yeah. So this is saying, okay, how do you know which one is the larger one? Where we're saying, okay, this function should return true when the first average is less than the second average. Okay. We just do that, and then now we have a lambda function. We can just pass in that function, and yeah. All right. Who's ready to see who the best and worst performing students are? Because I am. All right. So don't forget we have to dereference the students, so min student and max student. And I've also I essentially overloaded the printing operation so that it prints really nicely. So you will see that soon. Okay. If your name is listed, raise your hand and you'll get one of these, because I feel bad for using you as an example. What's happened? Okay, those are warnings. Oops, not supposed to print everything. Okay, so it says over here. Over here. Are either of you here? Okay.
I'll be Giselle.
Okay, so
Oh.
yes. Wait, are you the max
Yeah.
student? Congrats! Round of applause. Okay, what color?
I'll get purple.
Purple. Okay. See, you get candy without doing anything, other than get the highest score in the class. Sure. All right. So yeah. All right. So you can all see that this finds the min and the max. Okay. Let's try some more complicated questions. Average. How do you find the average grade? Okay. So it's your turn now. I want you to find the average of these numbers and these students. Okay? And for reference, my solution for the first one is 1 line of code long, excluding the print statement. And then for the second one, my solution is 2 lines of code. All right? So on your own right now, or if you don't have your laptop, discuss with your partner. Figure out how do you find the average. And as a hint, you can probably Google this. There's a function called accumulate, which might be helpful. Accumulate STL. I'll just put it up here.
Oh yeah. But that's the thing.
All right, actually, I totally misjudged the time, so let's speed ahead. So accumulate essentially just adds everything up. So if you just did the normal numbers.begin, numbers.end, and it also takes in a third value, which is the starting value. So I'm just going to say 0. This gets you the sum. All right, and what we can do is we can just say cout, the average is just that divided by the number of students, students.size. Okay? Questions? Okay, and then for the second one, we can do something similar. But the thing is, we can't really just add we can't just add to students easily, right? So here, you'd want to write a lambda function, add student, which essentially appends a student to a total running count so far. So for example, we can do something like this. Const. I think we start with the capture first. S. We start with a student and also a sum. And then we return the sum plus s1.average. Okay? Whoops. Then we can find cout. The average is accumulate students.begin, students.end, 0. And then also pass in the add student. Okay. What this does is it's basically keeping a running count of sum, and it's just going through all the students and adding them one by one. Okay. Does this compile? I might have to switch these orders. It does. All right. Do you all want to see what the average grade is? Oops. Might have to switch these. Switch these. Expected declarer. And the average grade is why is that 477? That's odd. I forgot to divide. Students.size. Okay, anyways. You get the point. There's a function which can accumulate everything. All right, so yeah, the average here is a 71. Wow, that's low. Just a fair warning. I think the midterm is probably going to be hard. Okay. Let's talk about finding the median student.
Wait, why just switch S1 and sum?
So I think what the function does is it basically takes, it goes through each element, and it takes in like the current sum, and it looks at each student, and it basically adds them together.
Yeah, and one thing I might add is you'll notice that when we're defining these lambda functions for the STL algorithms, like Avery is putting them, for example, in this case, you have to put them in exact order, and you might be wondering, okay, how do I know what parameters I need that will be valid to pass in as a function? The way that you find that out is actually just in the CPP reference. So if you searched up accumulate like C++ STL, you'll see something that says op, and in that it'll give you a function signature that describes what the function needs to look like. So it's sort of another case where we're working with interfaces in C++. But that's how we know what sort of functions we need for each type of algorithm.
Okay. All right, now let's work on this finding the median. All right, so one simple solution is to just sort everything and then find the middle element, right? That's finding the median. But you all learned about Big O. What's the runtime of that? Actually, you haven't learned about the runtime of sorting, so never mind. But yeah, it's n log n, which is not great. So we're going to try something better. There's an algorithm called the nth element. And what that algorithm does is you pass in the begin. You pass in a begin and an end. But the second parameter here is specifically the index at which you want to sort. Okay, but this is not fully sorting. This is only partially sorting. It's partitioning so that whatever element that you're pointing to right now, after the call to this algorithm, it's going to ensure that whatever element is at that position is in the right place. Everything to the left of it is less than that element. Everything to the right is greater than that element. Let me just rephrase that one more time. You're given a start and an end, but you're also given an iterator to one position. What happens after the call to the algorithm is everything to the left will be smaller than that element itself. and everything to the right will be greater than the element itself. Okay? Question, yeah.
What about if there's elements equal to it?
Yeah, then they'll all appear in like a middle section. Essentially, you'll form 3 different sections: less than, equal, greater. Okay, so we specifically want to partition that directly in the middle. So we're going to create a partition so that the one in the middle, that's the one you want to partially sort by. Everything to the left of that is less than the median. Everything to the right is greater than the median. Okay, that's a little complicated. If that didn't fully resonate with you, try looking up the nth element, and you'll be able to see like a demo of how it's running. All right, but what that allows us to do is this runs in O of n time, and then you can just do that, and it finds the median. The median was Nathan. Is Nathan here? No? Okay, too bad. All right, let's figure out who failed. Okay, I'm just gonna go through this quickly because this is pretty easy to understand. To check out who failed, well, you can create a predicate function that says, okay, if your grade is less than 60, then you failed. And then there are a couple functions you can call. One is called any of. Want to guess what any of does? Yeah, is there any element that satisfies the predicate? So did anyone here fail? The answer is, did I not print it? Okay, I might not have printed it. Oh, it's at the bottom? Okay. Did anyone fail? Yep. And then there are other functions you can call, like find if, which is basically find an element that satisfies this condition. Okay? Franklin? Who's not here, so no candy. And then finally, there's an algorithm called, suppose we wanted to find everyone who failed. What we can do is we can essentially, let's talk about that right now. What if we wanted to find everyone who failed? Okay, so one thing that we could do is there's this algorithm called copy if. So we can do something like this. Whoops. We can do something like this. We create a vector called failed students, and then we're gonna go from begin to end. We're gonna copy stuff into failed student dot begin, and then we're gonna pass in this predicate, failed students. Okay, does everyone follow so far? So you can imagine what copy if does. It basically looks through a range. Every time it finds an element that satisfies the predicate, it copies it into the some other iterator. Okay, this does not work though, and I have a demo. I have a really nice looking slide to explain why. So, okay, so let's say we want to copy instead of copying all the failed students, let's be nicer and say, okay, let's copy all the freshmen. Okay, so what's going to do is it's going to go through begin, and it's going to just go through and keep adding elements to begin. But what happens now? We're going to keep adding and adding. Oops, did I? It's going to keep adding and adding and adding. What do you notice? Sorry? So notice the elements here. They're actually being written into uninitialized memory, because this vector over here, when you try to copying stuff into that iterator, the iterator itself doesn't extend the containers. Does that make sense? Okay. So in the code right now, it says we're inserting into failed.begin, but as you're inserting, it does not extend the container if you run out of space. It's just going to start inserting stuff. That's a problem. Okay? The way around that is there is a special kind of iterator which will not only write stuff to a container, but it will also extend the container if there's not enough space. Okay? Those are called iterator adapters. An iterator adapter is a function that takes in an iterator and it spits out a mutant iterator which does some extra thing. For example, in this example, we're taking in the original iterator, fail.begin, and we're going to pass it into a function called backInserter. That's odd. No. Is that not what it's called? BackInserter. Yes, it's called backInserter.
You might need to import something.
One sec.
You need to import iterator.
Iterator. Okay, that compiles. Here, backInserter. All right, so we put in backInserter, and what happens is you will get back an iterator. I think I know why. Because you have to pass in the whole collection, and it returns an iterator to the back, which every time you try to write something to it, it extends the container. Does that make sense? These are called iterator adapters, functions which take in an iterator and returns a mutant iterator. Okay, so there's a back inserter, there's also a front inserter, and I think there's also like a general inserter which you can insert to any random location. All right, this is a very common thing that you'll see where if you want to populate like an empty vector, you have to use back inserter so that the vector itself actually expands in size. All right, any questions? Yeah, go ahead.
Just a quick syntax question.
Mm-hmm.
When should we write student.begin and begin student?
Yeah, so, good question. So begin students, there's an STL function called begin students, which all it does is it calls students.begin. Yeah.
So is it like the kind of iteration?
This is really just a function. Yeah. I think both are fine, although I initially started off writing this, and then now I noticed, there's not much of a difference. My only concern is that some collections don't have .begin, but the thing is if you're calling the begin function, that implicitly calls student.begin. So it doesn't really matter. Yeah, you can use either. All right, question, yeah.
So the implementation of backInserter does the associative iterator thing for you?
Mm-hmm.
Okay.
Mm-hmm. All right, any other questions? All right. Last thing I wanted to talk about. Okay, we are almost out of time, so I'm not going to talk about this curve, but this curve is kind of interesting. It uses this function called transform, which essentially you can apply a function to every element. Okay, so here what's happening is there's this function called Jerry curve, which takes a student and outputs another student. The old student is the original student, and then the new student is the same student, but their grade is curved using this formula. Okay? This is the actual formula that Jerry uses. Yeah, okay? And then how I found median and max, well, I calculated it up here. All right? Why do I have to include max and median in the capture clause? What happens if I just remove these? Yeah, these variables are not defined. Okay, because these variables are located in the outside scope, and creating a lambda creates like an inner scope. So you have to make sure you capture these variables. All right, and yeah, the Jerry curve is pretty generous, but not generous enough. Okay, any questions? Okay, let's do the Hamilton example. So I'm gonna I don't want to type this code, so I'll just basically explain the code, and then I'll explain what it's doing. Before I get to that, I want to quickly explain what stream iterators are. Oh, I don't have slides on that. Okay, great. So stream iterators are interesting in that you can actually create iterators to streams. And then they behave exactly as you expect. You can write to it, you can read from it, depending on if it's an input or output stream. And then you can use any of the algorithms on these streams themselves. Okay? So for example, one of the fancier ways to write to cout is to do something like this. This line over here. Copy. We're going to copy every student. And we're going to write it. Don't forget the third parameter of copy is like an out iterator that you want to write to. Instead of writing it to like a vector or something, we're going to write it to this thing, what it does, this is a stream adapter. It takes in some stream, C out, and it creates an iterator for it. So here it's creating an iterator for C out. Okay, so what happens here is it's going to copy all the elements, all the students here, and it's going to write it into an iterator that's pointing to C out. So what does that do? Yeah, it goes through each of these students. It's writing them into C out, and C out just prints it to the console. Okay, that's actually this whole thing over here that you see. Students sorted by average after Jerry curve, and you can see that, oh yay, 100. All right, well, yeah, you can see all the students are now printed. Okay, does that make sense? Okay, what questions do you have right now? We have enough time to get to the Hamilton example, so questions? Okay, so let's talk about this. So what's going on right now is I'm going to create a stream full of censored words. Okay, I suggest don't click into censored words if you're if you are offended by censored words. Don't click into it, but I did not come up with those. I downloaded it online. And since this is recorded, I'm not going to open that document. Okay, here I'm going to create a set of those censored words. All right, so what's the normal way to create a set using the words from a file? You all know how to do that, right? It's you open a file, you read word by word, and you insert it into a set. All right, but here's an even faster way. Just create an input iterator of the stream itself. IFStream is a stream, and just read it just pass it directly as into the constructor of set. If you look at the constructor for set, it can take in an input iterator. It can take in 2 input iterators, which means just go through that range and read all the words from that range and put it into the stream, into the set. Okay, so that's what you see over here. This just means read until the end of the stream. Okay, and then here we're going to create 2 more streams. One opens Hamilton, the other one opens a Hamilton out. So you can see over here, make sure I don't click into that. Yeah, this is the entirety of Hamilton. And an abnormally high number of students submit this for n-grams. Okay. And then now I'm going to create this function called shouldCensor. All right, so shouldCensor is going to take in a word. It's going to try removing some punctuation, and then it's going to essentially go through these different checks and determine what to do. So if it was able to find a censored word, then return a string with the same length, but with asterisks instead. Okay, I add this extra check because sometimes the censored word is followed by a punctuation. So I also made sure that if you have a punctuation there, then also censor that word, but still include the punctuation. Okay, and then lastly, we just return the word itself. Okay, what are some things you notice about this function? One thing you notice is what is its input? It inputs a string, and what does it output? Another string, right? So it's reading an element, and then it's doing some conversion, and then it's outputting another string. That's kind of like processing each word. It's going through it word by word, and it's going to process it using this function. Okay, that's why we call this function transform, which essentially is going through the entire set, and it's going to write to this iterator. This iterator is coincidentally, it's a stream iterator that's connected to the output stream. Okay, and then shouldCensor is what we are performing on each element. Another thing to notice is we're passing the censored words by reference. Simply because censored word is a set, we want to make sure we don't copy it. Okay? All right, any questions about this code right now? This is some very dense code because, but it's also really short. It's essentially doing like a very high level way of how do you actually go through and censor a bunch of words, right? The very mechanical way is, okay, have a while loop, read word by word, and then for every word, do this conversion. This is a more high level way to see it, right? It's, okay, we're creating, we have an input, we have an output, we have a transformation, and then we just want to go through the input, write it to the output, and apply the transformation. Very high level. You don't do any deep, low level details. So if you run this, I actually ran it many times already, you'll get something like this. Where is this? This is in downloads. It's written to a file, so I have to look at the file. Maybe it's in the build.
While Avery's looking for that, one syntax thing I want to clarify about this, like about the file reading exercise. Something you guys may have noticed from assignment 1, if you did it, was that when you're using IF streams and OF streams, whereas with the Stanford libraries, when you're working with files, they always emphasize that you have to manually call something like file.open file name. IF streams and OF streams automatically call open for you. So that's something small in case we didn't catch that from an earlier file lecture.
Okay, so this is the censored version. If you know anything about Hamilton, you'll know that these are censorable words. Cool, right? This is better than Cynthia's Hamilton example. All right, just a fun thing. How many of you watch Jimmy Kimmel? No one? One person? Maybe? Okay, so he has a segment called Unnecessary Censorship. Y'all know that segment, right? Some of you? Okay, well, unfortunately, I can't play it in class because it's kind of inappropriate, but there's an example. I was reading through this, and then, let's see. There was this really funny sentence. Here. This sentence over here. Okay, so if you know Hamilton, what is the word? What is the real word here? The real word here is escort, right. which is I mean, depending on the context, I guess, but this is definitely not a censorable word here. But I don't know, this sentence just sounds way worse by censoring it. Okay, so yeah, you get to see like fun things like here. You should read through this, and it's kind of funny. Okay? All right, any questions about the code?
One other thing is that, Avery's just shown you a bunch of useful STL algorithms. You guys can look up all of the possible algorithms that there are yourself online. So if you search up C++ and then the algorithms header, so like,
here.
Yes, Avery will pull that up right there. So right there, you can actually read through it, and they have it categorized for you, and you can see what are all the possible things that you can do now. Because now we've essentially completed all our entire STL unit. So you guys know what collections exist, so what data structures you can use to hold data. You now have algorithms that you can use to process those data structures really quickly and really simply. And so if you guys remember the first example that we did in the very first STL lecture, you guys can now do that. You have all the tools to do that. So yeah, next time we'll do sort of one general example of the STL to bring everything together, and then we will be moving on to some more modern C++ concepts.
And just an FYI, the solution to that code that we saw is set difference. Okay, so take a look at that code, see why it's set difference. All these algorithms are implemented to be the most efficient possible. So they use optimizations that we won't even learn about. So definitely use the STL libraries when possible. Okay? All right, thanks for coming.
And come get a donut. We'll bring the donuts right outside so we don't bother the people coming in.
Hi.
Everything we need to do assignment 2.
Yes, we are up to everything for assignment 2.
Okay.
Yeah.
And that's to be released Thursday, right?
We'll release it at the end of the week. Yeah, go ahead.
Okay, and then 2 weekends.
Yeah, you'll have around, I think it's 2 weekends. Yeah, around
Okay.
2 weekends. Yeah.
All right, thank you.
No problem. Yeah, go ahead.